Hi, everybody. Hi. Thank you very much, everybody, for coming out today. It's really awesome that we're back here in person. This is the, I think, 6th or 7th now co-op exhibition. And for the last few years, we've been doing it remotely through the GatherTown platform, but it's really great to have everybody come back and actually be here in person. So thank you all. Let's see. So we're going to quickly go through some introductions. We're going to do the flash talks. Flash talks are 1 minute that the student have to give as an introduction to themselves and their project and attract our attention to go over and talk to them. The poster session will last until 1:30, and then there'll be an award ceremony. There are these QR codes strategically posted underneath tables and behind chairs. Please scan it on your phone. It's just a Google form, and please do vote for your ranked candidates. And then we will issue a poster book once the event is complete. So thank you first and foremost to the awesome turnout we got. We got 22 student participants. That's fantastic. Thank you very much to Corporate Comms for the support and for broadcasting this right now. The Academic Partnership Program is hosting us. That's through Gina Strati, and we're doing a lot of things through there. And the Port Hope administration for supporting the travel for 2 Port Hope students to come up here too, which is really great. I have to apologize. There are other remote students that couldn't make it up. This is one of the trade-offs between having it in person versus having it virtual. It has to be an ongoing discussion. We have to figure out what we're going to do. So my sincere apologies to the students who were, unfortunately excluded for that. Oh, and sorry, I should also thank very much Payman Sadie, who's over there. He's trying to hide for the help organizing, and Mike Bach, who couldn't make it today. So just some notes for voting, just in case you need some criteria, but really give your honest impression about how easy it was for you to understand the topic, how enthusiastically the student presented themselves and the research topic. And please do take the time to vote. I'll try and position the QR codes elsewhere around too. So without further ado, we'll start off with the Gatling gun of presentations here. So thank you very much. Yep.
Hello, everyone. My name is Kanwani Asefa. I'm a chemical engineering student from the University of Calgary, and I've been spending my time here at the Hydrogen Technology branch, conducting a technical economic assessment of a hydrogen electrolysis plant that uses proton-conducting solid oxide electrolysis cells. The main goal for this project was to come up with estimates for the total fixed capital costs, or the CapEx, and the manufacturing costs, the OpEx, and compare that to previous work done by the branch for oxygen conducting cells. This was done with the use of process simulation software such as Esfand for both processes, in which I could estimate the equipment sizes for the plant and put them into a costing model that I helped develop. To learn more about what I've been doing this past summer, please visit my booth. Thank you.
Hi, I'm Spencer Bandiera. I'm going into my 4th year of engineering physics at McMaster University this fall. This past summer, I've been working under the applied physics branch in the experimental safeguards team to help develop a neutron source localizing detector array using compressive sensing. Compressive sensing is a fairly new sample processing technique that smushes measurement information and is able to then extract it through optimization techniques. This is important because there isn't an existing technology that is able to both localize 2 or more neutron sources and discriminate between neutron energy levels. So through optimization techniques and detector efficiency modeling using GEAN4, we are able to extract neutron spectrum information in addition to localize them throughout a polar radius and resolution. So that I've been working on doing the detector efficiencies and the optimization algorithm construction this summer. So please come check out my poster. Thanks.
Hi, I'm Leah, and I've been working in the Hydrogen Technologies branch over the summer. So over the past 4 months, I've been working on developing solid oxide electrolysis cells, or SOECs. So through the processes of high temperature steam electrolysis and high temperature steam co-electrolysis, we can use these cells to develop produce hydrogen and syngas, which are both clean energy sources. So to produce these SOECs, we produce these ceramic powders, which are then created into electrode inks, which we can screen print onto electrolyte substrates and then sinter at high temperature to plate the cell. So then these cells are then characterized to verify the material composition, porosity, and thickness of the electrodes. And then we can test those in our high temperature steam electrolysis units to verify the cell's performance. So over the summer, we've been using various material combinations and compositions to improve our cell's performance. Thank you.
Hi, my name is Ryan. I'm a mechanical engineering student, and I spent my summer with the Transportation of Dangerous Goods team. So my role with T2G was to help CNL assess our on-site transport capabilities for highly radioactive material. It's important for CNL to understand this not only to ensure continued safe operation of the site, but also for future projects that will require RAM to be moved around. The way that we do this is with shielded containers called flasks. They provide not only biological shielding with their lead and steel construction, but also security to ensure that in the event of an accident, contents aren't released. If you'd like to learn more, please come talk to me. I'd be happy to answer your questions. Thank you.
Hi, everyone. My name is Alexi Bonaventura, and I'm a fifth-year material science engineering student at McMaster University. Now, as nuclear workers, we are well aware that uranium dioxide powers most civil reactors around the world. However, on top of being incredibly hard to source in its powder form, conventional sintering and pressing methods are not proven to be a great method to manufacture these pellets. So, additive manufacturing is a potential solution to this problem, and here's where my team comes into play. We've been working on custom powder formulation using freeze granulation paired with a fused deposition modeling technique to print 3D ceramic parts using a zirconia surrogate material. So if you're interested in learning how we're planning on translating that to create uranium dioxide powder, please visit my stand. Thank you.
Hi, I'm Kurt.
And I'm Catherine.
We're students with Process Mechanical Engineering, and we're working on the CRL Configuration Recovery Project.
So every time a system is built on CNL property, each maintainable, repairable, or operable piece of equipment is assigned a tag number. And sometimes what's built in the field doesn't always match what's built or designed. And so it's our job to make sure that each item has a tag number associated with it.
Now, why is our job important? Well, first of all, according to the CSA standard N286, any nuclear site requires an asset management system. So CNL needs a working system to be able to function according to code. Second of all, we actively save CNL money because by doing regular maintenance on equipment, which is enabled by configuration, we prevent system-wide shutdowns.
So in the future, when doing any design work, please remember the importance of tagging so that we don't end up with a backlog of 40,000 tags again. Thank you.
Hello, I'm Carly Frank from the Waste Processing Technologies branch. One of our current projects is developing sustainable technology to treat mixed waste streams. Mixed waste is an expensive problem in our nuclear industry, and we are working to alleviate the problem by targeting select components and degrading them in an eco-friendly, sustainable, and cost-efficient way. Organic components of mixed waste include oxalic acid, which is used as a complexing agent. However, too much of this can actually inhibit further steps in the treatment process. We were able to photodegrade 95% of an oxalic acid solution using UVA light and various titanium-based catalysts. And we're hoping to continue this momentum by developing more advanced or modified catalysts, such as nanotubes, to improve our efficiency. Thank you.
Morning, everyone. My name is Selena, and I'm a sustainable chemistry student from McMaster University, and I'm also part of the RP branch from the Port Hope Area Initiative. So a big problem we're facing right now is that our efficiencies are decreasing as we're going from a planar source to a disk source during calibrations. And this decrease in efficiencies is bad for two reasons. One, when it's less efficient, you're spending more time doing this and counting, which impedes work. And two, like this uncertainty is just not desirable. So my proposal is that we should be improving the instrument design by changing the scintillating material to something that is more perceptive to lower energy alphas, which is what our calibration source is, which is UNAT. So that way, when the gap is smaller, as you can see here, it's easier for the electron to be bumped from this band, which makes it more efficient at lower UNAT efficiency, energies. Thank you.
So my name is Trevona. I am at the Radiobiology and Health Department of CNL. This summer I worked on characterizing acute myeloid leukemia or AML cells based on their cell surface antigen expression. More specifically, I used RT-qPCR as a technique to study gene expression of CD33, which is an antigen that is being studied by CNL for the Targeted Alpha Therapy or TAT project. That basically involves conjugating a CD33 antibody with actinium-225, which is an alpha emitter, to specifically target and kill only the cancer cells that are expressing CD33 and leaving the healthy cells alone, thereby minimizing side effects. So this graph basically shows us that AMLs, which highly express CD33, their graph starts way earlier compared to Jurkat's, which is a T cell line that don't express CD33 at all.
Hello, everyone. My name is William Little. I'm going to my 4th year of engineering physics at Queen's University. And this summer, I had the opportunity to join CNL's portable muon tomography group. If you don't know what muon tomography is, it's a non-destructive imaging technique known for its proficiency in identifying high Z and high density materials. Now, when I arrived at CNL, I was shown a long and tedious data processing, analysis, and imaging procedure. And my objective was to streamline this process. As a result, I developed an automation program that has now been seamlessly integrated and successfully tested in the lab with the system. It's a large step forward for the project, and I'm looking forward to seeing what comes next. Thank you.
Madeline Richards, and I am a co-op student with Property Remediation and Restoration of the Port Hope Area Initiative. The goal of the Port Hope Area Initiative is to remediate, manage, and safely store long-term radiological waste, following past practices by a former federal crown corporation known as El Dorado Nuclear Limited in relation to the refining of radium and uranium. Property remediation and restoration is divided into interiors and exteriors. I work primarily with the interior remediation team to remediate radiological waste in residential and commercial buildings. I also work under exteriors with Task Order 3 to remediate and excavate contaminated soils on residential and commercial properties. And in addition to this, I also am with radon mitigation, which is an interim measure prior to remediation to reduce radon levels at properties associated with low-level radioactive waste. If you're interested in learning more, come see me on my poster.
Good morning, everyone. My name is McPherson. I've been working with mechanical equipment development. As I'm sure we all know, developing the technology to produce actinium-225 is a major priority for CNL. And one of the ways to do this is by irradiating radium-226, which is quite rare. Fortunately, CNL has an inventory of legacy radium therapy devices, which can be repurposed rather than left to waste. Devices need to be declad or broken apart in order to access the isotope inside. So we've got a decladding machine. We've got a magazine container that fills and feeds into the decladding machine, but we need to get those devices into the containers themselves. So my colleagues and I have been developing a tool to feed the devices into the containers in a safe and reliable manner. If you'd like to know more, you can find me over at my poster. Thank you.
Good morning, everyone. I'm Alex Madison from Mechanical Equipment Development. The NRX reactor has now been shut down for 30 years and it will need to be dismantled. Part of this process is inspecting the internal parts of the reactor and collecting samples to determine where the waste needs to go and what kind of radiation fields are expected during decommissioning. The Mechanical Equipment Development branch is designing tools to enter an access hole through the side of the reactor and collect samples of graphite, the calandria vessel at the center, and also take radiation measurements. A plug lifter tool will connect to a 275-pound outer plug in the door and lift it out of the way to allow access to the central hole. Another tool will collect graphite samples by grinding graphite from the inside of the access hole and sucking the graphite powder through a vacuum tube to a collection chamber. These tools and many more will collect valuable data and samples to ensure the reactor is decommissioned as safely and efficiently as possible. Thank you.
Medical physics at McMaster University. My project for the summer was to optimize the process of RP instrument evaluation. So to implement strong radiation protection or RP controls at CNL, the radiation protection program recognizes that facilities need access to the appropriate tools to help protect themselves from radiation. One of these tools is RP instrumentation. I created a procedure to help streamline the process of RP instrumentation approval, and this will help facilities obtain approved RP instruments more efficiently. And this will also help ensure that these new RP instruments will meet CNL's high standards for safety. I applied this evaluation process for 2 contamination monitor, a hand and foot monitor, as well as a whole body monitor. And so through this process, I learned the importance of RP instruments and how it saves the company money in the long term and helps ensure that CNL remains the leader of innovation. Come see my poster over there. Thank you so much.
Hello, my name is Madeline Richards, and I'm a mechanical engineering student from Queens. This summer, I helped design hot cell equipment that'll be used in the production process of actinium for target alpha therapy. To produce actinium, we are irradiating radium that will be placed on a target and covered by a foil. This target will be sent away and irradiated and then returned back to site. When it is returned back to site, we'll need to remove that actinium from underneath the foil. So I helped design, build, and test equipment that will hold the target, seal to the target face, cut the foil as the target material, supply acid to dissolve that material, and then send the solution to a chemical processor. And once that solution is back in the chemical processor, it will extract, refine, and polish the actinium, which will then be used for target alpha therapy. Thank you.
All right, hi everyone. So in recent times, there's been a notable surge in cross-border movement of materials and resources. And so because of this, ensuring the prevention of unauthorized radioactive materials into the country becomes really important. And so to do this, we've placed radiation portal monitors all across the borders of the country. But because of low energy resolution, high background noise, and varying weather conditions, it becomes a really difficult process to identify and classify these materials. And so this is why machine learning models come into play. And so, hi everyone, my name is Deanne. I'm a 4th-year physics major at York University. And over the last 4 months, data processing as well as building an accurate machine learning model to help identify and classify isotopes with radiation portal monitors has been my objective. And I look forward to explaining everything in detail to you over at my poster. Thank you.
Hello, everyone. My name is Paul. I'm a 4th-year mechanical engineering student at University of Guelph, and this is the engineering jobs database for decommissioning and environmental remediation engineering. This is meant to be a one-stop shop work management tool utilizing Power BI and pulling information from the P6 and ECC database, meant to be used for DNER clients, resources managers, among others. The purpose of the tool is to be able to pull information directly and create a filter out all unnecessary information to show the most pressing data and tasks to do without pulling manually from databases. It is meant to be a comprehensive automatic tool to save time and resources for managers and resources. If you have any questions, please feel free to come to my poster. Thank you.
Hi everyone, my name is Louisa LaSenko, and I'm an engineering physics student at McMaster University. So this summer I've had the opportunity to work on 2 very exciting projects at the Applied Physics branch. So we're developing radiation detectors for border security applications, and I've worked on alarm and muon-induced neutrons. So what we're trying to detect is special nuclear materials that are fissionable and emit high energy neutrons. So these two detectors work on two very different principles, and I'll give you a little overview of how they do it. So liquid argon is alarm is a liquid argon radiation monitor, and it relies on the scintillation of liquid argon as it interacts with radiation. And my work has been to characterize the photomultiplier tubes. And for the muon-induced neutrons, they rely on the interaction between muons that come from cosmic rays with special nuclear materials and then we can detect the neutrons resulting from those interactions. So if you're interested in hearing more about this, please come to my poster and I'll tell you all about it. Thank you.
Hi, everyone. My name is Emily Woodcox. I'm an environmental technician student at Algonquin College, and I've been working here with the environmental monitoring branch at CRL as their summer student. So my poster's topic is working towards truth and reconciliation through CRL's first look at Indigenous traditional foods. We looked at fiddleheads, raspberries, and blueberries for gross alpha, beta radionuclides, organically bound tritium, and free water tritium. And while this project kind of started as a side task this summer in any free time we could kind of find, I'm hoping that through conversation today, CNL will expand on this idea to add it as an annual report in working towards truth and reconciliation in the area. Thanks.
Don't want to block my slide. Hi, everyone. My name is Hallie Wren. I'm currently a student at Queen's University in the biology program, and I've been working here at CNL in the radiobiology and health department. So I'm here to talk to you today about my summer project, which I did on radiation's influence on the cell cycle. So you can see here in real time, this is what my project would look like. So the cell cycle is the most crucial mechanism that the cell undergoes. It enables growth, division, and duplication within the cell. The cycle can be divided into 4 phases, which you can see in this circle here, starting from G1 and going clockwise. Gap 1, synthesis, gap 2, and the most well-known, mitosis. So this summer, we were able to utilize fluorescence to track the cell cycle after exposure to high and low doses of radiation. And as you can see, we had some pretty interesting results. So if you're interested in learning more, I'll be over here at my poster. Thanks.
Hi everyone, my name is Celine Yang and I'm a materials engineering student from McGill University. This summer I've been working in the plasma technology lab, and one of the projects I'm helping with is to generating the post-explosion particles using a laboratory scale DC plasma torch. So these post-explosion particles resemble those dispersed from radiological dispersal devices, also known as dirty bombs. It is important to trace back these radioactive materials' origins. For this reason, these particles we produce will be used to develop analytical techniques for post-explosion nuclear forensics. And the direct current plasma torch we're using can produce very sufficient high temperature to simulate the explosion conditions. Moreover, the thermodynamic studies has also been conducted using fact stage, and we ensure the potential reactions are endothermic and safe. If you're interested, come check out my poster. Thank you.
So thanks, everybody. That was the Flash Talk session. Happy to announce now that the posters are open. Please don't forget to vote. I'll have the QR code back up here again, or there are posters around. Thank you all for coming.